This question is about liquid flow. The diagram shows a storage container for liquids. So we have, here's our container. You can see here that it's going straight up there and then it curves out, and then you've got your liquid pouring in there. And it says the container is filled from above. The distance between the base of the container and the ground is h0. So you got your container there, there's your h0 there. And we have our height there. And obviously your height is going to increase as your liquid increases, the amount of liquid increases. So let's go to the questions then. It says here that the container, which is initially empty, is then filled at a constant rate. So when you're talking about a rate, we would be talking about the amount of fluid per second. So it's a per second value. A rate is always a per second. The height h of the liquid surface above the ground is measured as a function of time. The results of the measurement are shown plotted below. So we've got, this is our height in meters, and this is our time in seconds. Now, just to redraw it, remember the shape is something like this, and then it's straight down like that. So in the beginning, because your volume will stay the same, it will just be a function of the height, we imagine something happening up to from there to there. But as soon as you're going from this point over here, we would imagine that there would be some sort of change. So here we have our graph. It says draw a best fit line. Now remember again, a line does not have to be a curve, although for some of this we would expect there to be a straight line. Now in drawing this, you need to make sure that your line goes through all the error bars. As long as it goes through all the error bars, it's possible. So something like that would be fine. Hopefully you will do it a bit better than me. It will be a bit smoother. So going through all the error bars, and it should be fine. B, it is hypothesized that H is directly proportional to T. State and explain whether this hypothesis is correct for the periods time T is equal to 0 to 120 and greater than 120. Now just to remind ourselves, for a proportional graph, it's a graph y is equal to mx. It's a graph that goes through the origin and it's a straight line. So if it's proportional, it must go through the origin, it must be a straight line. So from time t is equal to 0 to 120, now that's up to there. Now this looks like it's a straight line. It's a straight line, but does not go through the origin. Not go through 0 point. So no, it's not directly proportional. And then greater than 120, we're looking at this section of the graph. No, it is not a straight line. And also obviously it does not go through the origin also. Then it says use the data from your graph to determine the value of h0. Now h0 is, remember, if we just remember our diagram, I just draw it over here. h0 is from that position over there. So that is when you started off time. That's when it starts to begin. So it's where this passes through. So it's somewhere over there. The value that you should get would be about 4.2 plus minus 0.1 meters. So when you do it on your graph, you should get about 4.2 plus minus 0.1 meters. Should be your value there. And I think you can see that because each one of these is 0.1. It's 0.1, 2, 3, 4, 5. You're going to 4, and then it's 0.1, 0.2. So we're around 0.2, 0.3 would be the value. Then it says D, the area of the base is 1.8 meters squared. deduce that the volume of the liquid entering the storage container each second is approximately 0.02 meters cubed per second. So we're going to use this portion because this portion we know up to there. We know that it's going to be rising at a constant rate. The h per time will be constant. It's this section of my graph here. So what I have to do is I need to find an h, a meters per second value, or a h over time value, and that is my slope. My slope of my graph, m, is equal to your change in your vertical, change in y over your change in x, or in this case, m is equal to your change in h over change in time. Now, what you have to do here, though, is you can't just use this. You must extend this line across your graph. Try and use as much of the graph as possible, and then construct for yourself a triangle. So I'm going to construct for myself a triangle there. Now, because I'm working on this whiteboard here, it's not all that accurate, but this over here will be your change in your h, and this will be your change in your time. When you work that out, when you do that, you should get a slope of around about, when you find that, you should get a slope for the graph, and m here for the graph should be about 0.012, and that would be meters per second. Now that's how quickly it's going up. Now if we know our formula for volume, it's equal to area of the base times by the height. So we're going to have the area of the base. The area of the base is equal to 1.8. So you're going to get your volume per second, your rate for the volume would equal 1.8, and that's going to be meters squared, times 0.012 meters per second to negative 1. Notice here that you've got a meter squared and a meters. You multiply them out, you're getting a meters cubed. So you're getting a volume, and you're getting a per second. That's giving you your rate. And when you multiply 1.8 times, when you multiply that out, you get about 0.022 meters cubed per second, which is approximately equal to that. Then it says, finally, the container is completely filled after 850 seconds. Calculate the total volume. Now, we've got here that our rate, the rate, which is the volume per second, is equal to 0.02 meters cubed per second. And we're told that it's 850. So the volume, the total volume, would equal just 850 seconds times the 0.02 meters cubed per second. You can see your seconds are going to cancel out, and you're just going to be left with meters, which is a volume. And when you do that, you get to approximately, it should be about 17 meters cubed. If you use the more accurate value for 0.02, you would get about 19 meters cubed. So it would be around about that value. It then says in F, the empty container is now filled at half the rate in D. Using the axes, sketch a graph to show the variation of height with T for the range 0 to 900 seconds. Now, because it is being filled at half the rate, we know that the slope of this graph, the change in height over the change in time, is going to be less. So I'm actually going to go to the original graph and work with that, because you'll be able to compare it. It would be quite good for you to have, in doing this, just to make a diagram of the original one, then you can compare it. So here's my original one. It's something like it. I'll just redraw it like this. Now, because it's going to half the rate, the slope of this is actually going to be half. It's going to get to 5.5. If this is 5.5, it's going to get there in about double the time. So, for instance, it took over here about that amount of time to get to there. Now, that's for the straight part. This is for the straight part before it goes like that. Getting up to there, which is a straight line, it would take half the time. It would take double the time because you've got half the rate. So, it's going to take about that over there. So, we're going to start off, we're going to be about there. You're drawn in a different color. It's going to be sort of a straight line there, and then it's going to curve around, and it's going to be like that. You would have something like that, and it's obviously by 900 the height will be much less because you're putting in half the amount per second.